Welcome to the weekly dose of science. Today we are going to talk about some new gallium-based materials with crazy properties. Gallium is a metal that turns liquid at near room temperature, with a melting point of around 30 degrees Celsius. Gallium is capable of forming several eutectic systems with even lower melting points with a number of other metals. One example is gallium, which is gallium mixed with indium and tin. Both pure gallium and these gallium-based liquid metal alloys have high surface tension, are difficult to spread on most surfaces, and stains many materials, leaving behind a nasty mess. This renders them difficult to handle, shape, or process, which limits their potential for real-world application. However, scientists have found a way to turn this liquid metal into a paste or even a putty-like form, like this silly putty that is shown here. This was done by mixing gallium with various forms of carbon such as graphite, graphene oxide, silicon carbide, or diamond powder. Like silly putty, this new composite can be fashioned and molded into any shape that we want. This recent discovery may have unlocked the possibility for broader use of gallium in the field of functional materials. First, we will explain what a composite is. A composite is a material that is produced from two or more constituent materials. A common composite that everyone is familiar with is concrete. Concrete is a composite that is made using cement with sand or gravel. In the case of the new gallium putty, liquid gallium is equivalent to cement, while carbon is equivalent to sand or gravel. The following video shows the creation process of the material. First, the gallium is melted and the carbon particles are added. The particles mix with the thin oxide layer on top of the gallium to get incorporated into the metal. The particles must be of the right size for them to successfully form the composite. Too small or too large-sized particles will not work. The resulting form of the composite is changed in accordance with the amount of the filler particle that is added, with larger addition resulting in increased viscosity. The amount is different depending on the type of particle. As for graphene oxide, 1.6 to 1.8% content results in a paste-like form. The addition of up to 3.6% graphene oxide results in a silly putty-like form. The resulting composite has some interesting physical properties. The material is extremely heat resistant, as it can withstand a blowtorch for a full minute without any structural damage. It is also possible to customize other useful properties by changing the composition of the filler particles in the composite. For example, using graphene oxide as the filler particle gives the material a powerful electromagnetic interference shielding effect, or EMI shielding. This property is of great interest in both civilian and military sectors alike, since EMI shielding offers protection against solar activities, EMP attacks, or electronic warfare tactics such as jamming. A 13-micron thick coating of composite on a reduced graphene oxide film was able to improve the film shielding efficiency from 20 decibels up to 75 decibels, which is sufficient for both commercial and military applications. However, the most remarkable property of the composite was its ability to provide EMI shielding property to any everyday common material. The researchers demonstrated that a similar 20-micron thick coating of the composite applied on a simple sheet of paper yielded a shielding efficiency of over 70 decibels. Perhaps the most exciting property was the high thermal conductivity of the composite when diamond particles were incorporated into the material. The thermal conductivity experiment showed that the diamond-containing composite had bulk thermal conductivities of up to 110 watts per meter Kelvin, with larger filler particles yielding greater thermal conductivity. By comparison, Arctic Silver Premium Thermal Paste only has 8.9 watts per meter Kelvin thermal conductivity. The thermal conductivity of the composite exceeds that of even liquid metal products, which performs around 70 watts per meter Kelvin. The reason why this composite performs better than liquid gallium is due to the excellent thermal conductivity of the diamond, which can be up to 2000 watts per meter Kelvin. The application experiment further proved the gallium-diamond mixture's effectiveness as a thermal interface material between a heat sink and a heat source. Interestingly, the composite with smaller-sized diamond particles showed superior real-world cooling capability despite having lower thermal conductivity. The reason for this discrepancy is due to the larger diamond particles being more prone to protruding through the bulk gallium and creating air gaps at the interface between the heat sink and heat source, reducing its effectiveness. The researchers note that there may be some ways to solve this issue in the future to further improve the performance. Thank you for watching this video. Please subscribe to our channel to get notifications on our latest exciting videos on science and technology. In addition, feel free to check out our other videos at any time.